Take a look at how to derive the equations of motions for the harmonic oscillator from the Lagrange equations, from the Euler-Lagrange equations. So if you remember, in a previous video I had shown that the Euler-Lagrange equations are given by the following. So they're basically d by dt partial L partial x dot, and this is partial L by partial x. And if you remember, L is given as the kinetic energy minus the potential energy. So the kinetic energy for a particle is actually just m times x naught squared half. And now for the potential energy varies usually only with x. So in this case we're only considering one dimension, so the potential is a function of x. Now for the harmonic oscillator, the potential of the harmonic oscillator is just 1/2 kx squared. So the Lagrangian is given by m times x dot squared half minus 1/2 kx squared. So if we take the derivative of the Lagrangian with respect to x dot, we get m times x dot, and if you take the derivative of the Lagrangian with respect to x, we get kx. We get minus kx. In fact, we get minus kx. So yeah, so if we now plug this into the Euler-Lagrange equations over here, we get d by dt of m times x dot, and this is minus kx. And now usually we assume that the mass m is not a function of time, it's just a constant. Then we have m times d by dt of x dot is equals to minus kx, or we can also write this as m times x double dot is minus kx. And this is the equation of motion for the harmonic oscillator. To calculate the actual trajectory of the harmonic oscillator is very simple. I'm not going to go through it here, but I'm just going to briefly mention that the solution to this differential equation are just trigonometric sine and cosine functions, and we're going to have a look at how to solve this equation exactly in another video. So we have derived the equations of motion for the harmonic oscillator from the Lagrangian, from the Euler-Lagrange equations, using this expression for the potential energy, and we get indeed the correct equation of motion, because basically the acceleration is negatively proportional to the distance. So for example, if you have a spring and then a mass attached to it, so this has spring constant k. If I pull this mass towards the right, then it's going to experience a force in the opposite direction, right? So this is the force. You're going to experience a force in the other direction. So this is the displacement, delta x, and then or basically just x, and then the force is in the opposite direction, which is minus kx. And since the position of this mass is just x, we have that m times x dot, m times x double dot, this one over here, is just the acceleration. So indeed we have derived the equation of motion from the Lagrange equation, and we have now verified that the equation of motion follows Newton's second law. Okay, that's it. Thanks.